Here's an interesting fluid mechanics problem that is something which, if you're a first year engineering student, you might see in your fluid mechanics module. So, at its core, this is actually just based on mass conservation and continuity. And it's a relatively more difficult problem than the average, I think, because there's some integration that's going on which may not be obvious at first, but as we'll read the question and as we'll start solving it, you should see what I mean. So again, this is the kind of question that you might see in your first year, most likely if you're doing something like mechanical or aerospace engineering. And if you'd like to see anything similar to this on the channel, let me know in the comments. So what we're actually looking at here is a cone. So this is technically a 3D problem, right? So this is the cross section of the cone that we're looking at. And we've got this water which is coming into the cone through this bottom part. So you have water going in through here. And then what happens is that the level of the water inside the cone is obviously going to rise. However, the way in which it rises will change over time, if that makes sense, because for one, the velocity of the water at the inlet is a function of time. So we know that V is equal to K times T. So K is a constant, which means that the the water at the inlet is in a way accelerating uniformly. And as a result, the speed of the water, the speed of the free surface is also changing, but also this is a cone. So in other words, when the water level is here, as shown in the diagram, versus when the water level will be here, it will move in different ways because this surface area will be bigger, and if the surface area is bigger, it will move slower than when the surface area was this big. So basically, the velocity of that free surface is always going to point upwards. And my prediction is that the velocity, although it will always be upwards, it will decrease over time. And we have to find this sort of relationship between the variables. Or more specifically, we have to find an equation for the height of the water. So let's see how we can do that. Just remove a couple of things from the diagram. So what we have in front of us is just an equation of mass conservation, right? So we can simply say that m dot is constant because that's what mass conservation tells us. So I would say that m dot in is equal to m dot out, but then we have to decide exactly what's in and what's out. So what I would do is I would probably just draw a control volume, right? So I would draw a control volume like this, and I would make the control volume cut through here, and then I would have, so this is, the shape of this control volume is like the body of the cone. It's not an entire cone because, it doesn't have a vertex per se. However, there's an important thing which the question tells us, which is the fact that this diameter here is much lower than well, I would say than the height. So we're being told that if D is very small, right? So this is an approximation that we're going to use in a bit, and I'll show you how exactly we're going to use this approximation. So this is what we're looking at. We have water going into this cone, and we want to find how fast is that free surface moving upwards. So let's first find the equation for m dot in, right? So mass flow rate in is going to be density multiplied by the area multiplied by the velocity. So I'll just call it rho AU for now, and then we have to decide what's what. So I'm gonna write that this is equal to rho, which is the density. The area is, of course, the area of the pipe that the water is going through, and this is a circular pipe, so we're basically looking at something like this, right? So this is the pipe, and this pipe has a diameter which is, lowercase d, which means that the area is just pi over 4 d squared. So I'm gonna write the area as pi over 4 d squared multiplied by the velocity, which is given to us as v, right? This v here. So this is rho and then pi over 4 d squared, and instead of v, I'd have capital K times t. So that's it. That's the mass flow rate that goes into this cone. So what we have to do now is write what the mass flow rate out is going to be. So we have m dot out. So that's the density. Now, because we're dealing with water and water is a liquid and liquids are incompressible, then the density is going to be the same. And we're going to have a different area, and then we're going to have a different velocity. Let's call this v out. Okay, now let's talk about the area for a second. So the area that we're looking at is basically the area which is over here. So that's the area that we're considering, which is the area of the base of the cone, and the base of the cone is a circle. So let me actually try to draw it here to understand what we're actually trying to find. And this circle has a radius, let's call it r, right? So this r is essentially, just remove this for a second, and the radius r is basically this. Okay, and that's the radius of the circle. So the area out is just pi r squared, like this. And then what we have to do, because actually we don't really know anything about the radius, but the question tells us that there's an angle here which is theta. So that's the angle between that outer surface of the cone and the vertical, and that angle is going to be constant, obviously, right? So we can write here that theta is a constant angle, which is obvious because that funnel isn't actually changing its shape, so that angle is going to be there all the time. R, however, does change its value, because if you think about it, as the water is increasing, so for example, when the water reaches this point, the radius is going to be, from here to here. So the radius increases as the water advances upwards. So we don't really have anything about R, but we can get a relationship between a couple of variables, and those variables are going to be R, theta, as well as H. And we should try to get something in terms of H, because H is what we're trying to find in the end. So if I try to draw the cross section, which only involves R and H, this is something that, well, this is what I'm going to end up with. So this is R, and then basically I'm looking at a trapezium here, like this, and then this angle would be theta, and this height here would be H as a function of time, right? And this bit here, if you look at the diagram at the top, this is half of that diameter of this pipe, right? So that would be d over 2. However, at this point, to simplify things, we can actually use this approximation that the question told us about at the beginning, which is that d is very small, basically. So what would mean in that case is that instead of dealing with a trapezium, we're just going to deal with a right triangle. So we have a radius r here. This diameter, this d over 2, I basically condensed it into a single point. So we have a right triangle now, which has one side r, one side is h, and this angle is theta. So we can get a value of, well, we can get an expression for r. So if we use some trigonometry, we get tan theta is r over h, right? So we know that r is going to be h times tan theta. So that's going to be our radius, essentially, right? So that's it. So what we can then do is we can find what the area out is, which is here. So we have area out is pi r squared, and r is this, therefore this is pi h squared and then tan squared of theta. Okay, so that's our that's the area of the base of the cone, base of the inverted cone, I should say. And the other thing we have to use is V out. Now, we don't really know what V out is, but it's okay because we can express V out in terms of H, right? Because if you think about it, in general, the speed or velocity is the rate of change of distance. So in this case, the velocity of the free surface, we can write it as, so V out is the rate of change of height. So this is just dh by dt, or you can call it h dot if you want, but I'll just leave it as dh over dt because I'll have to separate some variables in a bit. So that's what V out is. So what I'll do now is I will write M out as rho. So that's the density, and then we have the area, which is pi h squared and then tan squared theta times the velocity, which is dh by dt. So that's our M out. And if you remember, we also had M in. So M in, we got it somewhere here. So that's this bit here. So it's rho. So it's rho pi over 4 d squared, and then it should multiply by kt. And that's everything. So that's M in and that's M out. So the only thing left to do at this point is to just, put the two, create inequality. So we have M in is equal to M out due to continuity. So if we equate the two sides, this is what we're gonna get. We have rho and then pi over 4 d squared kt. This is equal to the mass flow rate out, which is rho pi h squared and then tan squared theta dh over dt. So I'm gonna remove the rows. I'm gonna cancel out the pi's, and I think that's everything we can cancel. So now we just have to solve this, because remember, what we're trying to find at the end is an equation for, or an expression for h, for the height of that, column of fluid as a function of time. So let's try to do that. So on the left hand side, we have d squared over 4. Remember, d is the diameter of that pipe that, is connected to the funnel, to the cone. And then this is kt, which is equal to h squared, and then we have tan squared theta dh over dt. So this is a first order ordinary differential equation that is relatively easy to solve. We can just separate the variables, and we'll do that in a bit, but I just want to show you some of the steps beforehand. So what I'll do is I'll put all the constants on the left hand side. So we have d squared over 4, and then we have k, and then, well, the other constant is the tan of the angle, so that's, well, the tan squared of the angle, and then multiplied by time, and this is equal to h squared dh over dt, like that. So we're gonna separate the variables, and the variables, of course, are height and time, right? So we can, it's easy to separate. So all we have to do is keep the h's on one side. So I'm gonna have h squared dh on, well, the left hand side in this case, and this is equal to all those constants, so d squared over 4 times k over tan squared theta t dt, right? And then we can integrate both sides, so I'm gonna integrate this and this, and we're gonna have h cubed over 3 equals d squared over 4 and then k over tan squared theta t squared over 2 plus a constant. So we have this integration constant that we have to deal with, but we can because the problem tells us that at time equals 0, so basically when you start counting the time, h is 0. So in other words, you know, the level of fluid starts from here essentially. So if we use that, so I'm going to say that h of 0 is equal to 0. It should be pretty straightforward, the fact that 0 is equal to 0 plus c, therefore the constant of integration is just 0. Okay, so finally we can write that h cubed over 3 is equal to, so I'm going to combine the 4 and the 2, so we have d squared over 8, and then we have k t squared over tan squared theta, and finally h cubed is 3 over 8 d squared k over tan squared theta times t squared. So we could leave it like that, or we can just write h as a function of t equals, and then 3 over 8 d squared k over tan squared theta t squared, and this is basically the cube root of this, or I can just raise this to the power 1 over 3. And this is an expression which gives us exactly that. So it gives us the height of that water column as a function of time, and as you can tell, everything else is a constant. So just as a reminder, this is the diameter of the inlet pipe, and then this angle is the, well, I'll just call it the angle of the cone, and k is just some constant. Okay, it's actually the acceleration, but we'll just call it a constant, and t is time. So this is essentially a simple, well, I wouldn't really call it the simplest mass conservation question, but it's just one inlet, one outlet, and then there's a bit of calculus in the middle. But that's the end of the question.